Okay, in this short little section, we're going to look at modifications to the traditional silicon MOSFET structure. First, we can talk about using other materials and nano objects in the channel. And then second, we can talk about how to turn the MOSFET into an element of memory. And this is critical for the NAND flash memory that's dominating the market these days for solid-state hard drives as well as little thumb drives, USB drives. So first, let's look at nano and exotic channels. So we're going to imagine our traditional MOSFET, except we subtract all the silicon. So we have our source metal, our drain metal, and our gate metal. Maybe we can have a gate oxide or insulator here too. And now that we've subtracted away the silicon, we can put whatever we want in that channel. So let's look for a minute at the expression for the transconductance. The transconductance of the MOSFET depends on the width, the mobility, the capacitance of that oxide here, and in the saturation regime, solely on the V gate source minus V threshold. And this is assuming a common source configuration. So what can we change here? We can change some physical parameters in terms of the sizes of things, the lengths and widths, which we've talked about in the last section. We can change the thickness of the oxide, but only up to a point. So we can start to put some exotic materials in to give us better transconductance. So the capacitance, remember, of the oxide is simply the, if we take it on a per area basis, is simply the dielectric constant divided by the thickness. Sometimes this is also talked about in terms of K, and K would be 1 over this. So we can put in so-called high K dielectrics. So instead of silicon dioxide, we might put hafnium oxide or other things that have a large dielectric constant. That gives us more charge control in the channel. Now, the other variable here is the mobility. Silicon has a rather large effective mass for electrons and holes compared to other materials. So we might want to select some materials that have a higher mobility, either because they have lower scattering or because they have a lower effective mass. So what are some candidates? Well, we could put in materials like indium, gallium, arsenide into the channel and grow these FET structures epitaxially with very thin channel layers. The mobilities in the gallium arsenide, indium gallium arsenide system can approach maybe 5,000 to 10,000 centimeters squared per volt second, compared to the 1,500 or so for silicon in the best case scenario. So replacing silicon with other semiconductors can work. Other options, more exotic things, carbon nanotubes. So these are whiskers or thin tubes or pipes made out of carbon where the carbons are bonded into a sheet and then rolled up and connected into a tube. And the fundamental structural unit is a hexagon of carbon. And it turns out that these can have very high mobility along their length for certain types of nanotubes. So this research was very intense in the 1990s and 2000s. And recently in the 2010s and beyond, it's turned into a sort of modified case where imagine if you slit this carbon nanotube and unfolded it, you would get what we call graphene. So graphene is a form of carbon sort of like an infinite sheet of carbon with the structure in plane defined by these hexagonal rings again. And again, graphene has very high mobility as well as exhibiting some other more exotic physical effects. So you can make very high mobility channel transistors out of graphene. The problem is it's not very useful for digital logic because it's impossible to turn off. It turns out that graphene is a semi-metal, so it's actually impossible to form a depletion width inside the graphene or totally depleted of carriers because the conduction band actually touches the valence band on the EK diagram. So the best case scenario is that the Fermi level is right here, and in that case you would have thermal excitation of some holes and some electrons at any operating temperature except for 0 Kelvin. So that means you'll have two types of carriers in the channel in the best case scenario where they're at their lowest concentration. If you apply a voltage and move the Fermi level up through this EK diagram, you get a lot of electrons, which can increase your conductivity very greatly. However, you can never turn it completely off. And that's an important distinction with the silicon-based ones, which are useful for digital logic. Now, you can form other materials that are like graphene, where instead of a single type of atom, you form mixed or compound semiconductors. So boron nitride was one that was tried first. It turns out that its band gap is rather too large to use effectively. So recently, some nice transistors have come from the molybdenum or tungsten chalcogenides, meaning sulfur and selenium bonded to this metal. And these form pseudo two-dimensional structures, sort of like sheets of atoms that are a little bit thicker than the case of graphene, but they do have a band gap and thus can be gated on and off, just like silicon. One last case that has been made into transistors would be semiconductor nanowires. So instead of growing, say, epitaxial layers of indium gallium arsenide, you could actually grow a nanowire which looks sort of like a carbon nanotube, except instead of being hollow, it's actually filled with material. And the benefit to using a material like this would be, one, in terms of its large mobility in plane because it's made of a compound semiconductor, but then two, because if you put a gate on top of it, the actual physical dimension of this nano object is very small, and so you get very nice charge control over the entire volume under the gate. And so the switching ratio between the on and off states can be very high in a very small volume. So next, let's talk about how to turn a MOSFET into an element that can store information in a non-volatile way, meaning that you can turn off the power sources and the information will still stay there. This has led to revolutions in photography as well as speed of accessing information off of hard drives in the form of solid-state drives. So one of the main drivers for doing this was definitely the digital photography revolution. Suddenly people needed ways to store large amounts of digital data in a very compact form in terms of these memory cards. So let's go back to our basic MOSFET structure. And now instead of making the gate out of a simple metal, we're going to form a more complicated structure. So we could put some other polysilicon there, and then another layer of oxide, and then a metal. Now, what does this allow us to do? Let's look at the band structure of this region here. Essentially, just looking at the conduction band, we have some region here where the semiconductor is sandwiched between two layers of insulator. And this is a very large energy barrier, many electron volts. So there's virtually no chance in a billion years that the electron could leak out of this structure once it's put into this polysilicon layer. What can we do with this? Well, if we go back to our definitions on a parallel plate capacitor, we have our relation Q equals capacitance times voltage. The charge plus Q minus Q on this capacitor are directly proportional to the voltage. And really, you can, if you have a fixed capacitance here, now this is going to be the capacitance between this oxide and the channel. Charge and voltage are really the same thing. So if we can inject some electrons into this polysilicon layer here, and then we can turn off the power source, those electrons will be trapped for many, many years, stable, non-volatile, and effectively they'll exert a voltage on the channel. This means that we can turn this MOSFET on and off depending on the number of electrons that we've injected into this charge trap here. This could be called a floating gate type of arrangement. So how do we do this? Well, we can apply very large electric fields across this and rely on different mechanisms of tunneling in order to inject carriers through these oxides. And you can program the amount of charge in this, either drawing carriers from the channel or from the metal gate, depending on how you design your memory element. So what this means is, by sending a test signal, trying to establish a connection between the source and drain, the controller can say, memory element number 4080, do you have a digital 1 or 0? So if there's charge here, there's an inversion layer in our N-channel MOSFET, and thus you get a digital 1. And a 0 would correspond to no inversion layer, meaning that there's no charge there. So by applying sequences of right voltages, you can program this this type of MOSFET, which is sort of like a MOSFET combined with another gate on top of it. And you can permanently program the state of that memory element. Now, I did just say permanently. What I mean is permanently until you intentionally erase it again. You can drain the charge out of that by applying another sequence of voltages, perhaps at a slightly different level. So you have a write voltage and an erase voltage, which can switch your element between digital 1 and 0. So this, I hope, has just given us a little taste about extensions to the MOSFET technology. It can be used for different purposes, such as very effectively in cheap memory, and also we can look to the future and use more exotic materials in order to make faster and better performing transistors through the application of materials science.